Okay, so let me say welcome to episode 5 in the series of how to design electronics. So today's all about sensors. So there's been a bit of a storyboard to the events which we're running here, starting off with power supplies. Then we looked at was it logic? I think we looked at logic. We looked at op amps last time, and op amps are going to feature a little bit in today as well on sensors. So for those who are new, let me just share with you that this series with Makespace is all about sharing some tips and tricks for your own electronics. And everything I've got here to share with you this evening and all the previous sessions are all free to download. And I think this event might be being videoed as well by the good people at Makespace. So if you do want the downloads, if the video goes wrong, if you skip on over to my Silicon Cortex website, siliconcortex.uk, and just go to downloads, you will find there's a folder called How to Design Electronics. And the schematic of today's electronics and all these notes are already there. So you're free to download those at any time. So what I really want to do with these events is just give you a little bit more of an insight into electronics than the sort of foundation things that you can find on YouTube and in magazines. So this is hoped to be like a little added extra. So it is live. Anything can happen. I've already got one demo down, which doesn't seem to be playing anymore. But I'll fix that for next time. My name's Stephen Clemmet. I've been designing electronics now for good on 27 years. And if anything's not clear as we go along, or you want something else explained, please just interrupt me. I'll be happy to field questions. Right, so sensors. So what I've done for us, these are my slides. I do them on paper. So let's say with sensors, you can measure anything and everything. It's the interface between the electronics and the real world. And trust me, there is a sensor for it. So just to give you a flavor as to how many sensors there are, this is a quick list from DigiKey of the sort of volumes they hold in stock for different sensors and a rough percentage of what sort of market share they have. So accelerometers, I'm not sure what's going on here because they really should be the #1 sensor today. But they seem to have lost their crown when I looked at DigiKey. I knew temperature, audio, and accelerometers are usually top of the list for the most common sensors. And so they're the ones we're going to be looking at mostly this evening with a few extra bits because people have been asking me for different things to look at. So I wonder if there's just a procurement problem around accelerometers at the moment. I'm not sure. I did have to recheck my numbers because usually it's accelerometers and sort of temperature usually have equal sort of numbers, but it seems audio is currently got the crown. So anyway, it's just there's sensors for absolutely everything. I suppose the first top tip is if you're going to use a sensor, it's probably a good idea to make sure it's going to be available and in what volume it's going to be available. So it's nothing worse than designing something and then finding the thing you designed for is no longer available. We've all been there, I'm afraid. So there are really sort of, I'd say, two main types of sensors, really. There's digital, which I've categorized into logic and into I2C SPI, which is really for interfacing directly into sort of microcontrollers. I'm going to gloss over a little bit with I2C and SPI because I haven't yet had the chance to talk with you about I2C and SPI. That's a whole subject on its own. And when we get around to Series 2, starting in the autumn, I plan to give that a whole good section. But most sensors that you buy, certainly accelerometers, which we'll have a look at in just a moment, they all pretty much exclusively I2C and SPI. So we're going to have a little look at them, but we're not going to get tied down with them. That's what I'm looking for here. Digital logic sensors, I would say, are things like on-off switches. So I've got one here, actually, if you can see on the camera. I'm not sure you can buy these anymore. This is actually a mercury tilt switch in a glass envelope. So if you break the glass, I think I'm going to have a bit of a clear-up operation on my hands. But this is what I would call a logic sensor. It's kind of on and off. There's nothing wrong with that. It's just about picking the right sensor for the job, really. If you look at a lot of industry, which I've been looking at, like in manufacturing with big plant machines, most of their sensors that they have for, say, pressure, ultrasonics, for liquid levels, most of them really are just glorified on-off switches, nothing more than that. And that's probably because it's the ease of installation, the fact you've got long wires. So most of them aren't sending anything more than it's got a problem, it's time to stop and fix it. But for this session, I'm going to concentrate mostly on analog rather than digital. As I say, the reason for that is I don't really need to talk too much about logic about on-offs, and we haven't covered I2C. And analog ties in quite nicely with the op-amp session we had a month ago. So, okay, right. The most popular sensor in the world at the moment is accelerometers and vibration. And we'll have well, we were going to hook up this one to the computer, but it seems to stop working, but we're going to talk about it anyway. It's just the demo broke. So I've got here an actual piezo sensor, which we'll have a look at, which is just here. So this is what these things look like. And I've got an oscilloscope here with it all hooked up. So we can have a look at exactly what does the waveform look like from something like one of these. So these things are actually used in part, sometimes in things like washing machines for vibration, although they do also use reed sensors. I know Samsung are doing some great stuff with sensors. So I think if you just bear in your mind's eye that what we're going to hook up here, we're doing vibration first, right? So if we hook that up to there and this up to vibration for, yep, that's correct. So what does this look like as a schematic? Right, so this is my design for using piezo vibration. I've got this is my input here. So this is where I've actually got my sensor hooked up. I've got a buffer amplifier just on the input, and there's a DC block here. So it's a tiny bit of filtering, but it's really a DC block. So this is my sort of buffer amplifier. I've got a little filter here, which you could work out if you wanted to. We'll come back to that later if we have time. And then I've got an amplifier, and this amplifier has a gain of, we can write it down here, G for gain is 1 plus R3, which is this resistor, over that resistor, R6. So in this case, this gain is about 150. or 151, 150 kiloohms divided by 1 kilo ohm plus 1. It's about 150. So different sensors will have different voltages of requirements, of course. But let's do an experiment. And if I swap to, right, I'm going to have to run through my cameras here and find out which one it is. It's going to be number 3, probably. There we go. Right, so hopefully you can see an oscilloscope. Yeah. Right, let's just turn the time base up a little bit. Let's get it going a bit quicker. Oops. Hang on, something's fallen over. Right, okay, so, oh, hang on, the wires come out. One moment. The other thing I can tell you about piezo sensors is they are polarized. So if you do fit them the wrong way around, as I discovered, they tend not to work. Right, there we go, that's working. Right, a wire just came out, so I just had to put it back. Right, so if I, there we go. So you can see our time base there at the bottom. Oops. There we go. So let's get rid of that one. Right, so what I'm going to do with the sensor is I'm giving it a flick, which I'll show in a sec. So as I flick it, you can see that I get a response. So I'll come back to the camera in a moment so you can see that. So you can see it does respond quite nicely. But what I have found, just go back to that camera. So that was giving us a flick like that. Let's just refocus that. There we go. That's giving it a flick like that. And so in fact, what I can do now is, now you get that idea, I can just drop this camera in here. There we go. And there's a small camera in the bottom right-hand corner. So as I give it a flick, you can see that it's responding. But with these piezo sensors, if I was to do it gently, see, it hardly responds at all. So I think the first observation there is, you know, if you're using it as a bend sensor, it's not going to work. And if you bend it really slowly, it also does not respond. So these sensors are much better, you know, on a shock load. Just an observation there I've noticed. Right, the other sensor, which I can show you, which the demo's not now working, unfortunately, but doesn't matter. We can still look at it. Is called a Mem sensor. So this is the most common type. This is the sort that's in your mobile phone and, you know, any other electrical equipment. So it's quite easy to find some data sheets for these devices. Whereas with this sensor here, you can only bend in one axis because it's a film. It doesn't bend, you know, in any other way. If you've got an accelerometer, which I will simulate with a block. So this was our accelerometer, which actually on our board is actually this tiny little square just here. So I could just hold it up. So that tiny square is actually the accelerometer. So it's a fair bit smaller, yep, than the piezo sensor. But with accelerometer chips, is they could do the whole left-right tilts, and some of them go in 3 domains. So you can have the the Y domain, the X domain, and of course some of them will come out of the page in Z. So again, it depends on what you want to do. We will come back to accelerometers and when we talk about I squared C in a future edition, if you like. But say they're used absolutely everywhere, these devices. There's probably a procurement problem at the moment with getting hold of them. But again, with accelerometers, when you start going below 0.5 hertz, they start not working. So the holy grail of accelerometers is really low frequency. But the problem is that they stop responding at really low frequency. So one of the ways that they try and deal with this is by looking at the frequency domain and then starting to infer low frequency from high frequency harmonics. And when we did timers, we had a look at harmonics. I think that may be in our second outing. So everything will come around in due course, as we tickle along with various sessions. So, price wise, these devices can cost you about £4 for some of them, and they come in different flavors. I've got one here which is a little bit longer. So I wondered if this would be a bit more sensitive. It feels like it should be, but when I hooked it up, I found it wasn't any more sensitive to low frequency than this one. Whereas accelerometers usually have less than a couple of pounds. So these are, at least twice the price. So, and you've probably got just as much supporting electronics as what you have with an accelerometer. So I'm not entirely sure how much saving there is today to try and go with a piezo. Frequency response would probably be what would make you want to decide one over the other. Right, so so there's accelerometers for you. Most popular one by a long way. The second most popular sensor ever has to be temperature. So I've got a couple of temperature experiments on here which we can have a look at. So the first one I've got on here is, again, sticking with analog. This is a temperature chip which I've used a number of times. So it's this one just here. So it's a leaded part. You can get devices that will sit physically on the board. This is one here, which we're not worrying about this one today, but there is one you could actually put on the board as a component. This one here, this is a temperature sensor, signs of a bit of dust. So we'll have a look at that in a second as well. So if you're going with a chip solution, the lovely thing about using something like a chip is the output is usually, in this case here, it's this red line, which is device B, which is a TMP36. And for this one here, the output voltage, V0, so V0 here, so I'm going to do this. The output voltage, gives you 10 millivolts per degree. So you might end up having to put an amplifier on that in order to see some sensible deviation. So we can hook that up and have a look on our oscilloscope. If I put that on there, put that on there, right. So what I'm going to do is I've got a hot source here, which is my soldering iron. So we'll warm it up. And I've also got a can before map plane closed. I've got some freezer spray so we can cool the thing down. So I'm going to swap to a bigger screen for you all to see. Right, there we go. Right, so the big sensor. Right, so this should hopefully warm it up. And we'll start to see, there we go, we'll start to see it increasing. In fact, what I want to do is I just want to slow it down because I want to show you something interesting here. Right. What I want to show you is it's not all peaches and cream, because as it warms up, so now this is hot soldering line is about 400 degrees, and the sensor is very slowly warming. We'll just let it do a couple of units there on our oscilloscope. Right, and now I'm going to let it cool down. Now the ambient temperature is clearly not at 400 degrees around that sensor. So what we're seeing here on the oscilloscope right now, we can see just here, is this is it warming up. And this is latency. So the package has actually got quite a lot of energy stored inside it. So for fast energy transitions in temperature, this isn't really going to be very useful for us. And in fact, what we can see, if we just stop that there, so what we can see is that, oh, put my fingers off, the cool down to get back to ambient is longer than the heating up. And all devices have this latency effect. So that's with the bigger chip. With the smaller, hopefully this will work. With our smaller device, we'll come back to it in just a second. If I start running this, this might work. Oh, it didn't work. It just cleared it. Of course it did. Right. Never mind, we'll do it all over again. So this is the smaller device. So it's still heating up okay. And we'll just then see how long that takes to cool. This might cool at a different rate because it's got a smaller mass. So it'll probably cool a whole lot quicker. Right. And if we heat up the other device so we can have a comparison. Okay, why is that not now heating up? Because it's on the wrong device. Oops. Hang on a second, I've made a mess of that experiment. Right, not to worry, not to worry. Right, so with this smaller device, we'll just swap back to the other camera so you can see stuff. Here we go. Right, so what I will do, if I zoom in, there you go. Right, so that first one, which had quite a long cool down, it was this device here. And the other time it was this device here. So this has got a much smaller thermal mass. So you can see on this, on the oscilloscope, the cool down is a whole lot quicker the smaller the thermal masses. And I've also found with temperature sensors that if you try and measure the ambient temperature with a surface mount device on the PCB, because there's heat in the PCB, it will affect the temperature of the reading. So if you want to measure the environment, I find you're much better having the device on legs. If you want to go really fast sensitive, of course, we use a thermocouple, which we've not got here today. Right. So the other temperature sensor we were just playing with, this is the circuit for it. Oh, hang on, let's zoom out. Here we go. So the other circuit here, this was this one here we were just playing with, this much smaller one. So I've got a potential divider, and then I've got an amplifier. And of course, this is a non-inverting amplifier, where in this case, the gain is R9 divided by R11 plus 1. That's the gain equation for all amplifiers of this type, this configuration, I should say. And in this case, because these two resistors are the same, that means I've got a gain of 2. So what you'll probably find is that something like this is actually being supplied for you inside here with a little bit of more calibration to make your life easy. Something else I discovered whilst putting this together, which isn't on here because I only discovered it about sort of half an hour ago, is on the back side of this, I had to add some capacitors. I'll show you in just a second if you can see, but I've had to add a capacitor onto the output. Why have I had to do that? It's because I was experiencing some noise problems in the signal on the oscilloscope. When we talk about product reliability next month, we'll talk a lot more about the use of capacitors to solve noise problems on boards. But if you do have a noise problem on an analog circuit, chances are a capacitor in the right place, costing 0.1 of a penny, will fix your problem. So there's a top tip. Right, okay, ticking along, the third most common sensors we saw in our list at the beginning is audio. So in terms of audio, there are many solutions for audio. One I've got here is the one I've used quite successfully. It's a chip solution. So this is a Max 9814. You can get it from all good distributors. It's also available on a small Adafruit board, which is not that one. Oh, this is the one here. So this is a small Adafruit board here. So this is how I did the original testing, and it's been very successful. So I now use it in all my designs. I will hook that up to the oscilloscope in the moment because it's got some good features for sensing sound. But in terms of the circuit that you use, I haven't actually sat down and derived this at all. I'll be perfectly honest. They actually give it to you. So all these audio chips and everything, they'll always give you an application note on how to wire it up. And this is no exception. The only thing I've done is draw the actual footprint of how I want it to look. So I can't take credit for the circuit design, but it does work really well. So if you were sensing, say, like noise level detection, then this would be a particularly good way to, well, an acceptable way to do it. So we'll just hook this up and we'll see what's good about this particular choice that I like. Right, let's wind that up a little bit. There we go. Right, so what I've got hooked up, I'll switch to the bigger screen so you can see the oscilloscope better. So this is the microphone here. This is a tiny electric microphone. This is, and then this section just here, this is the Maxim chip, the 9814, and the rest of it's just the supporting capacitors and resistors. So let me just swap to a different screen of the oscilloscope for you. There you go. Right, so the one thing I do like about this, if you're using any audio work, is it's already biased at a, well, that's about 1.25 volts. So it's not biased at the 0 volts, which if you were then going into, say, a microcontroller, it would cause you a problem if you try to put a negative voltage into a microcontroller. Chances are the ADC will get upset. So as I'm talking to you, you can see the oscilloscope, well, the device is responding. And I'm probably about a foot away. You can adjust the gain. There is this gain control on the board. Let me just swap back for you. There we go. So this device, it's got like an auto gain control on here. So you can put a pull up or pull down resistor here on pin 10. And there's another feature here called, I think it's called attack rise. I've never read into it fully just yet. But you can configure this device just with pull-up, pull-down resistors. And then if you want to say the audio, the output here, which is so it says audio, that's what I've got hooked up to the oscilloscope at the bottom right of your screen. Mic here, that just means that loops back to that point there. And TH here, the mic bias, that loops back to there. This schematic's all available for you to download. You can get it off the data sheet, or if you go to the download section on my website, the schematic will give you the URL for the components. Okay. One thing, obviously, with audio as well, so which we won't touch on today so much is, but we'll again, I think this is warrants a session on its own. Season 2 is on filtering. So when I was a kid, I did develop using chips wasn't around in sort of 1985. My BBC computer, for those who remember those. I did as a kid, had an audio amplifier, and then I had a high pass and a low pass filter. And provided you spoke extremely clearly to it and didn't mumble, if you said yes or no, I had an audio-driven menu system for running through games on my BBC Micro. So I don't know what happened to that, but we will talk about filtering. Its own subject at a later date. Right, okay, let's carry on, shall we? So they're the 3 main sensors I wanted to share with you. I've had a couple of requests come in for talking about different sensors, which we'll have a look at just now. But before I do that, so this is kind of a generic circuit, which we're just about to use it for an experiment. And you could probably get away with this for most things. Again, it's just an amplifier. This is a variable non-inverting amplifier. Again, as we've been saying all along, the gain is just this top resistor divided by this bottom resistor, and then +1. The op amps I've chosen here, and they're in the schematic if you download it, will operate on a single supply rail. So that's a 0 volts up to, I think, something like 5 volts. So some op amps, as we discussed last time, you need to have a negative voltage. So you need what we call a split rail. We don't need to worry about that with this particular device. But I've got an experiment here. So Ruth, who's on the call, asked me last time about audio. What did we call it? Water level sensors. Is that right, Ruth? Your microphone's off, but I'm sure you're saying yes.
Yes, I did.
Right. So what I've bought here, at great expense from Amazon for about £4, is a company profile. So this is just a water level sensor. I've had a look at this circuit. All it is it's really quite disappointing. I'll tell you. So this sensor here, so we've got our 3V3, and I think this is how they've done it. They've got a resistor here, so I'm not sure what the value is. Then there's another resistor, which we'll call water. And then they've got that going into a transistor like that. So that's all this is. So this is just this is called an emitter follower configuration, where pretty much the output, which is this is the emitter, that's the collector, that's the base. The output for the emitter pretty much follows the base minus whatever voltage drop, which is usually about 0.6 for a common or garden transistor. So that's all this is. And you know, a lot of sensors. I mean, this circuit here actually is that this is an optical transistor, which circuit, which I put on here, just having a bit of a play, or a light dependent resistor, or even Adrian sent me a request to, could we talk about dissolved oxygen sensors? So we'll have a look at that in just a moment after this exciting experiment. So for this experiment, what I've done, I've gone to great pains to get some tap water, some distilled water, yep, and a glass of Guinness. I think it's important to have a balanced scientific experiment with a reward at the end of it.
Like it.
So, okay, so here's the questions for you. You might just have to make it up in your own mind. Right, so the question is, if I put this temperature sensor in each of these glasses to the same level on here, and it's quite an important point what we'll be seeing in just a moment, is do these liquids have any effect on the actual reading that we get? Okay, I'm going to swap the screen in a moment, and I'll tell you which ones we're sticking it into as we go. So you can see on the, hopefully then see on the oscilloscope. Right, so with my sensor, fingers crossed this does work, is I'm going to dip this into the tap water to the correct level. Right, actually, what is it? It's going to turn that to 1 volt. Right, so you see it jumped up there. So I'm just going to move the line. So this is our reference. So that's our reference point. So when I take this out, you see, obviously it does drop. Okay, just drying the sensor there of the contamination of tap water. Now, the next question is, if I put it in the distilled water to the same level, what happens? Do we go to the same level, below, or above? And this is distilled water. So this is actually the finest Halford's distilled water. Right, so I'm sure you've made your mind up what the answer is. Right, so, and the answer is to the same level. Guess what? It looks like it's slightly lower. So the moral of the story here is that when you've got your sensors, obviously you're going to have to calibrate for whatever the fluid is. So who would have thought there is a difference between distilled water and tap water? I can only guess. I'm sure somebody will know better than me that it's maybe the minerals within it. And right, and this last experiment here is the all-important Guinness. So Guinness is supposed to have an awful lot of iron in, so we're told. So the question is, if it's got a whole lot of iron, does that make it all the more conductive? Do we go above our tap water line, which is this one, or do we go anywhere different to our distilled water, or what? So make your choice. You've got 2 seconds. Made your choice? Good. Right, let's find out what the answer is, shall we? So it looks like Guinness has pretty much the same properties as tap water, I would say. I think for some of us beer drinkers, that might be disappointing. But there you go. So there's the answer. So I thought you might enjoy that genuine scientific experiment. I mean, you can also use, obviously, lie detectors work on this principle. So I'm just going to put my fingers on the sensor. As you can see, look, so obviously there's some resistance there. So if I was telling an enormous fib, my hands might start to sweat a little bit more. And I think that's the principle of most lie detectors. I'm not sure. Anyway, there we go. A useful use of a pint of Guinness, and something for me to look forward to doing something slightly more constructive with get the cat hair out, something more constructive with after the show, if you like. Right, okay. The last thing I've got here for you before I do conclude is, so where is it now? Adrian asked me about, I don't know if Adrian's on our call or not. If you are, make yourself known, unmute and say hi.
Hello.
There you go. Right. Good to be interactive. Right. So Adrian sent me a note and asked if we would be able to include dissolved oxygen sensors. So what's this for? Is this a fish tank thing, is it, Adrian?
It's more complicated. It's a bioreactor.
Oh, right. Okay. Right. Well, I've only had like a very short time to look at this, and I don't have one to hand to plug in. But the one I had a look at very quickly, again, you know, the analog, I've got an analog output, which we've been looking at today. And it's got an output. This particular one is 0 to, say, 3 volts. Not sure how well you can see that. Maybe if I zoom the camera in a tiny bit.
Yeah, it's visible. It's clear.
There we go. There we go. Lovely. Glad you can all see. So, you know, so different sensors, you know, I imagine the, you know, the point I want to share with you here, different sensors will, of course, have a different output ranges. We just saw using our water sensor and our Guinness experiment, you know, we were measuring, you know, I'm just looking at the oscilloscope measurement here, 1.8 to 2.2 volts. So going back, where's my circuit here? Hang on a second. Once I've used something, I cast it aside. Hang on a second. Boom, 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 boom. Oh, that one would do. Maybe. Oh, this one will do, just to hand. Right, so just going back to this circuit here for us, let me just zoom out there for you all. Right, so different sensors obviously are going to have different output voltage ranges. You know, if we're talking industrial sensors, they might be 0 to 5 volts. Other sensors I've worked with will just have 0 to 1 volt. So, you know, this particular one here is 0 to 3 volts. So if you're going into an ARM device, most ARM devices are, you know, 0 to 3.3, you know, with, say, you know, 10 bits resolution. You could probably, you know, provided, you know, I'll probably go through a buffer just so I don't have any impedance problems with my sensor. If I had a very low signal, you know, say it was 0.5 volt, like with the temperature sensors earlier, I would then probably want to have some sort of amplification, but it's always going to be unique per device. So what I've done on my setup here, I could have shown this to you, is this is actually a variable resistor, so I can actually adjust this 150K in my circuit. So it's kind of there's no one size fits all in terms of the amplification, but I do find generally that an amplifier of sorts, whether you have to have a split rail one, you know, and then get rid of some of the negative voltage, you know, and obviously buffer the input, usually will do the trick. Does that help you at all, Adrian, or answer any questions? Did you have anything in particular?
Oh, no, that's very helpful. Thank you so much. Yeah, it would be nice to see the URL for those for that board too, but that's very useful. Thank you.
Well, if you do go to my download section on my website, I say the schematics which I've got here and the notes I've shared with you, they're all there already as PDFs. So and you can also then go back to the one on op amps, and that'll fill in a few gaps on op amps, and then the op amp power supply, of course. If you need a split rail, you can wind all the way back to the very first one we did. I think it's last November. I think October, November, which talks about power supplies, which is which was what we introduced the series with. So so hopefully now as we're moving along, everything's starting to sort of to link to previous sessions, and and like with the vibration with the MEMS, the vibration that's actually linking to a future one. So we will double back to talk about this device, well, season 2, I suppose. So well, look, that brings me to the end of what I've got here for you today. The next one for date for your diary is May the 5th, same time, same place. It will be on reliability. So my favorite subject, EMC, we'll discuss. And if you do have any requests, by all means, just drop a note on the meetup page, and I'll do my level best to try and include it for you all. Well, okay, let me open the floor. Is there anything you want me to go over again, discuss, thoughts, comments? It's over to you lot.
How about sensors for specific gases?
Oh no, say it again. Sorry, John, line went funny.
How about sensors for specific gases? Thinking particularly of carbon monoxide as a safety sensor.
Yeah, I think with those sensors, well, a lot of them are particulate sensors, aren't they? If I'm correct.
I don't think it could be particulate for carbon monoxide because
no, that's true. Smoke, I'm thinking, aren't I?
Yeah,
I've never used them, to be honest with you. The stuff I've designed hasn't called for it. I don't know. Maybe I don't know if they have a shelf life. How do they degrade? Would be one of my questions. And if you know anything about degradation of those sort of sensors.
I've got a little tiny bit of knowledge here. It's not extensive. It matters a lot whether you're looking for CO in your gas dissolved in water or in the air. If it's in the air, then I'm afraid my knowledge dies. But in water or other liquids, it's really very difficult indeed to do sensing on a persistent basis. You can do it once or twice, easy, but then you have to reset the sensing. So that's my tiny contribution to the debate.
Okay, well, it's more than mine.
Stephen, I was wondering, the temperature sensors, the TMP3 series, you were saying the outputs is linear variable, the temperature received, that's variable. But I was wondering, how accurate does the input voltage have to be? Is it a case that the output scales with the input voltage, so you really have to denoise it? Or does the input voltage simply cap the output?
Okay, so I think, John, do you just mute your microphone there, John? There you go. There's quite a lot of interference there, John, on your audio. But I believe that's okay. I believe you were just asking about, when we talk about the, if I can find it, whatever I've done with it. When we talk about the temperature, I believe he was asking, I'm just trying to find the page. I believe he was just asking about how accurate the, oh, there we go, that's lovely. How accurate the power supply has to be.
Yeah, exactly. Whether you're going to have to condition the power supply very carefully for that to get an accurate output. In other words, whether the output scales with the input with the supply voltage, or whether it simply caps the maximum output.
Okay, if you should just mute your microphone there for us, because there's a bit of interference there on your feedback system. Anyway, yeah, so yes, so I would say that a good clean power supply, and it's one of the things we spoke about on our first outing together, if you like. A good clean power supply is very important, particularly with analog. And how clean that is, predominantly it comes down to, and we'll talk about this when we get to reliability next time, so I'll make sure we do cover this. A lot of it comes down to how you lay out your design. So, you know, Ruth, I'm sure, you know, like with decoupling, if you remember your decoupling circuit, Ruth, we had your capacitors all blocked together, and John Grant says, no, spread them out a little bit more. So, yeah, the layout.
Yes.
Yeah. So,
and in particular, put the little small value ones closest.
yes, exactly. So just going to draw on this circuit here, what I would do to answer John's question. So I always, very close to the pins of the power supply, I always add, oh, hopefully I don't run out of paper here. I always add some decoupling very close to keep noise out, because you don't want noise, John, to affect the quality of the signal. It's like a good old thing, you know, rubbish in, rubbish out. So yeah, so I always, and I tend to use ceramic these days for this purpose. I always put 1 nanofarad and 100 nanofarad in parallel, really close. And I do that on all my devices, you know, digital or analog. But also with, if you've got analog, I'll certainly be probably adding a bulk capacitor. And by bulk capacitor, what I mean is probably a large value. So it might be somewhere on my designs, somewhere in the order of about 100 microfarads. And it's all about trying to keep the power supply smooth and clean. In fact, why don't we have a look at what we've got on our design, shall we? Just see if we can have a look here. This is quite a simple board, so it might not be terribly representative, but you know, we can see if we've got anything worth writing home about. So that looks pretty clean, but what I'd probably be inclined to do to make sure my power supply is clean, if I remember how to drive an oscilloscope, I put it on AC and then wind it up a little bit to start looking for noise. And is that noise going to cause me a problem? So look, there's a little bit of noise there, but you know, it's not even 10 millivolts peak to peak. So I would call that a nice clean power supply. When I first actually made this board, I had to put some capacitors on the back side of the board on the output just here, because I was getting some disastrous noise. In fact, I'll tell you what, let's see if I can take it off and we can, maybe it will start to demonstrate exactly what John's asking if you get your power supply wrong. Hang on a minute, just doing some hardcore electronics here. Right, this may or may not make any difference whatsoever. Right, so there we go. Can you see that now? See all that horrible noise on the power supply, and that's yeah. So yeah, but that's coming off the output. So my input's clean, but yeah, there's something going on. So this was about 10 minutes before we started. I was just running through things, you know, just about 7:15, and I thought, oh my God. So I just put 100 nanofarad across the output, and everything quietened down. But, you know, it comes to the point, John, of, you know, a 0.1 penny component in the right place can make a world of difference to your design. And I think it's kind of experience that will help sort of, you know, shine a light on where to put the components Some years ago, I had a problem with a power supply design. I was having some noise problems, and I'm sure many of us know in Cambridge know Steve Wiseman. I think he used to be a Makespace member, and he told me put a 10 nanofarad capacitor in exactly the right place, pointed at the board where to put it, and boy, the problem just disappeared. So components in the right place is what you need. You know, if I'm doing analog and digital, I split things very carefully, and we'll talk about that next time. And I do power line filtering, planes. So it's quite a big subject, but yeah, you've got to keep it clean. Otherwise, you're going to end up like with noise, like we can see here on the oscilloscope for sure.
Thanks.
Any more for any more?
You've mentioned capacitors in parallel for keeping the noise out. How about inductors in series?
Yeah.
I vaguely thought from early days that that was supposed to be equivalent, although presumably not quite.
Absolutely. And again, you know, if you're going analog, yeah, like analog computers, yeah, which like for machine learning, I think, you know, analog computers are sort of slowly on the rise. But yes, so let me just get a clean sheet of paper. Right, so yeah, so what I sometimes do in my designs, there we go, that's an inductor. Can't think what value top of my head, but this is called a pi filter. So, because it looks like pi, I think that's why they call it that. So yeah, so I might have my 3v3 here, which I'll call D for digital. And then, yeah, I might then have A for analog, if that makes some sense. So yeah, I mean, and there's two ways to think about the inductor. Again, I've learned this one the hard way. Is you could think of using like a surface mount bead inductor, which is basically it's a ferrite, or you could go for something like a proper one, which is wire wound. I would say if you're worried about noise, go for the wire wound. Yes, it's more expensive, but you'll do a much better job of rejecting any noise. So yeah, absolutely, John. I'll often, you know, and if I'm taking any power off board or two sensors, yeah, my designs, like for accelerometers, for example, which basically is an analog device. It's a micro electromechanical device. Then I will actually probably use a proper inductor for sure. So yeah, good point.
The right value for that inductor.
I'm sorry?
How do you pick the right value for that inductor?
Yeah, I'm not 100% sure where to start with the right value. You know, I guess start with what you got in the drawer.
It's not a case of very carefully calculate your LC for each side of the network. It's
yeah.
whatever.
Yeah, I mean, you know, for EMC test site, you know, whether you go to ETF stebbing, which I use, or whether you go to DB up the road at Cottenham, you know, you've got a problem somewhere which you're trying to fix, and yeah, you tend to start with what's in the drawer. But you know, you'll be able to do a rough calculation, and just suck it and see. And what you have to remember with filtering, of course, again, another subject for another day, is when you're looking at things like capacitors for well, be impedance C and frequency. I think, what is it? I think they look something. I think that's the way. No, it's the other way, isn't it? It's the other way. It's the other way. It's the trough. So that the capacitor behaves at a capacitor up to a certain point, and then, you know, it starts misbehaving. So yeah, it's a whole new can of worms, you know, when you get to RF.
Stephen, it might be worth just mentioning why you might use a capacitor in series with your sensor signal.
In series with your sensor signal. Yeah, good point. Good point. We can go back to that here. Here we go. It's almost like we planned that, Ruth. Here's an example. So here it is in series. So it can act as a DC block. Which is a good reason, because if you're using it as a DC block and you've got an AC signal and you've got a DC block, then you might have to have a negative power supply, of course. So you do have to be quite mindful with why do you have a DC block and then a capacitor in series, and of course the value of the capacitor as well. That will probably depend on what sort of frequency you've got coming in. I mean, for audio, well, audio is going to be sub 40 kilohertz for sure. Accelerometers, are usually good up to, well, most of them, certainly the MEMS devices are good up to about 1 megahertz. If you want to go above 1 megahertz, they start to get quite expensive. So, yeah, or if you've got multiple stages in an amplifier stage for your sensor, you can then sort of, if you, how can I describe this? If you were to say have an amplifier stage, say that was times 10, and you went into another times 10, let's say. You don't want to end up saturating one amplifier, because if this amplified a signal sufficiently high such it was quite close to the supply rail because of a DC offset, then this amplifier here would probably just slam into the supply rails. So you could solve that just by AC coupling them and get rid of the DC components. That would be one reason why you'd want to do that.
I have another question, which is, what's the most difficult or alternatively most interesting sensor you've ever had to deal with?
Oh, the most interesting sensor? Blimey. Okay, I wish I'd thought of that one ahead. At the moment, I would say the most challenging one for me at the moment is actually MEMS accelerometers. The reason why is I'm particularly interested, some of the work I'm doing in machine learning for vibration. So if we can go back to this device here. So in fact, this is the one I'm using, can you believe? So trying to pick out, vibration noise from say a washing machine, like my washing machine, which is not very well at the moment. So trying to work out at what point, well, how can I describe it? When a washing machine's brand new, it's always nice and quiet, like getting a new car. But over time, it starts to develop a rattle in the washing machine. Like my one, Paul Freakley, who's on this call, we had a good discussion about bearings in washing machines, which is a problem with my one. So I'm interested in trying to model how to predict a bearing starting to have a problem, so it needs replacing before the wheels come off the cart, as it were. So that's using a MEMS accelerometer. I'm currently doing it in the time domain. I'm using RMS at the moment. Because you've got positive and negative as things vibrate, I want to take out the negative part component, so I'm using a root mean squared, which is quite straightforward to do. But the big challenge, of course, with accelerometers, which we haven't discussed, there's something called Stiction in accelerometers, which essentially means no one's quite sure what causes it. I think it's electrostatics in the microengineering, that basically the mechanical system just locks and gets stuck. And the only way you can free it is if you just tie everything to ground. So almost like a 100% discharge, and even though you've got tighter ground. So it's called Stiction. MEMS devices do suffer with this problem. And so in terms of solving a problem, I've had to put into code in the ARM core being able to, if it spots that the accelerometer's not recording anything, then it knows it just needs to depower it and restart the device. So that's a challenge. But yeah, that's my challenge at the moment is vibration.
Funny you should mention that.
Cool. I knew somebody who did their PhD studying friction, and it was only about 10 years ago, and he commented to me that, you know, by this time, you know, in the 21st century, you would have expected that all there was to know about friction would have been studied extensively.
Yeah,
he
but
said
not.
the answer was no, it wasn't. And actually, he specifically mentioned this point about Stiction as being something that really hadn't been studied at all.
Yeah, well, what's his name? Phil Claridge, his wife, I think her name's Anne Marie. I think that's they live over at Bourne, I think, which Camborne rather. There you go. When I grew up, Camborne didn't exist. And I think his wife Anne Marie's done a lot of research into Stiction problems as well, and it's a known problem. And I think some devices are more prone than others. And I think probably, you know, you could spend your whole life trying to find a device that was less prone, and then one day it will just stick.
Well, I think the point. Well, my understanding of it is there might be electrostatic forces involved, but it's a fundamental physical thing. So searching for devices that aren't prone is likely not to be helpful because, you know, by definition they all are.
Exactly. You'll be there forever and a day trying to find one that isn't. So
Yeah.
you're better off coming up with a solution like the one I've got here. And apparently the one I came up with, Phil Claridge said, yeah, that's what you do.
Anyway, so yeah, one of the suggestions, I don't know if this is a reason, but a suggestion is that Stiction is due to two surfaces settling closer together. You know, once they're static in relation to each other, that they settle closer together, and therefore you get van der Waals forces forming between them, which are of course nuclear. You know, what's it? The weak forces, and they make it harder than it would have been otherwise to move it on.
Yeah. So are you saying, Ruth, that no one really knows the answer still?
A lot of people have suggested answers that are plausible.
Okay.
Does that answer your question?
I'm pleased to say, whilst there are some plausible explanations, yeah, shutting the device down completely solves it. And on that note of Stiction is, when I was coming up with this solution to Stiction, which this device does suffer with, I powered the device down, but it still didn't fix the Stiction. And the reason why, it was back powering through the I2C port and just keeping the device in some erroneous state alive. So I then had to reconfigure the ARM I2C to be logic outputs, and then I could drive them to ground in order to solve it. So yeah, but yeah, a genuine problem.
Me of a problem. One of the devices that I've had a certain amount to do with is the TI AM3, I think 3358 devices as found on a Beagle board. And one of the things splattered all over the datasheet for that is do not, under any circumstances, provide power at a non-power pin when the device is otherwise powered down.
Yeah, there you go.
Words, don't do ever what you just talked about happening, because you may will damage the device.
Yeah. So I mean, even though obviously the I2C was, through destroying a couple of pull-up resistors, we know whether they were 2K7 perhaps, that there's still sufficient current to keep to keep the thing alive. Yeah. So there's a word to the wise.
I had that problem with a DVI cable into some kit, and the pull-ups on the source were enough to power the board when you turn the board off.
Yeah.
Or enough to break the reset circuitry, so when the power came on, it didn't reset. Yeah, it was a big problem.
Yes. Yeah. I mean,
Power.
it's a complicated subject, isn't it? Electronics. When you start getting, digging under the hood, a little bit deeper than, demo kits like which you can get for Arduino and Raspberry Pi and another. When you start trying to do it yourself, that's when things start to unravel a little bit.
Talking of cool devices, and this is completely off the topic, but anyway, on Twitter today, I saw a rather neat device. Somebody had put the processor from a Raspberry Pi Pico, the 2040, onto a 1-inch square PCB that included all of the output, all of the GPIO outputs, battery charging circuit, and a flash chip.
Mm-hmm.
And for a 25mm square device. And it was also castellated pins on the edge. So I thought that was rather neat.
Yeah. Making things small. There's definitely a trend for being as small as you can. I've noticed that.
Until you want to probe the resistors.
I'm sorry, say again?
Until you want to stick the scope probe on the resistor, the 0201 resistor.
Oh, yes. Right. Well, look, everybody, it's 8:45. I think we should probably wrap up and go and put the kettle on in our respective homes. I'll just remind you that, May the 5th, not May the 4th be with you, but May the 5th, day after Star Wars Day, is the next session. As it will be on reliability. So, some of the things we've been discussing today will definitely pop up. And if anyone's got any special requests for reliability, by all means, just drop it in the comments section on the meetup, and I will pick it up from there. Other than that, I guess I just thank you for listening to me ramble on, and see you all next time. Yeah.